very good morning and welcome to this course on the foundations of continuum mechanics. Today we'll be talking about the energy equation and then we will solve a couple of problems as a part of tutorial for week 10. So let us get started. So the law of conservation of energy can be stated as follows. So we say that the time rate change of the sum of the kinetic energy and the internal energy, that is kT and Et, is equal to the rate of work done by the different forces acting on the body plus all other energies that are entering or leaving the body per unit time. And all these energies entering or leaving the body may include heat, electrical energy, magnetic energy, chemical energy, etc. So this is our balance law for energy as a starting point to derive the energy equation. Similar to like we had the rate of change of mass equal to 0 in conservation of mass and the linear momentum principle or the Newton's second law in the linear momentum equation. So this is a simple balance which says that the sum of the rate of work done by all the forces and all the energy entering into the body is going to result in either the increase in kinetic energy or storing the energy as an internal energy or both. Let us express this into a mathematical form. So the left hand side we will call k dot plus e dot, and we'll talk about these k dot and e dot soon, is equal to, so first we write the rate of work done by the surface forces, which is this closed surface integral over the bounding surface of the body. So the rate of work done by a force is F dot V, force dotted with the velocity. So this is di vi d gamma. So this can also be called the rate of work or the power delivered by the surface forces. Then we have the work done due to the body forces, which will be an integral over the volume rho bi vi times d omega. And this is the rate of work or the power delivered by the body forces. For the present consideration, we will talk about heat, which can be written as a surface integral because the heat or the heat flux typically enters from the boundaries of the body, like you're heating a body over flame or you contact a body with a hot or a cold body. So that is energy transfer from the bounding surface of the body. So this can be written as a closed surface integral over this bounding surface of some heat flux vector, so which has units of watts per meter squared. So that is the rate of energy entering per unit area. So this has to be multiplied by an area, and since this is a vector, it has to be dotted with an outward normal. So this becomes Ni. But since we have an outward normal, so if Qi Ni is positive, that means heat is leaving the body. So to ensure that we are talking about energy entering the body, we have to change the sign here. So this quantity is called the heat flux. And to this, I add another term, which is a volume integral, which includes all other energy that's being either generated or being lost from the volume elements inside the body. So an example of this could be an interaction with the electric field that results in the heating of each and every volume element in the body. So typically when we consider only heat transfer, we talk about resistance heating, or heat being generated inside the body is typically taken as a volumetric source in the energy equation. So let us label this equation as equation A, which has the mathematical form of the rate of work done by the forces acting on the body and all the energy that's entering or leaving the body. Now let's talk about the left hand side, which involves the time rate change of the kinetic and the internal energies. So the kinetic energy as a function of time can be written as the sum or the integral over the complete volume times half times dm, the mass of a small volumetric element d omega, times the magnitude of the velocity squared for that element. So this is the total kinetic energy as a function of time. So k dot, which is the material derivative of k. Now if you look at this, you can see that this vi is like an A star, which is an intensive quantity per unit mass. So from our discussion on the material derivative of integrals, this becomes half rho, and then we have a dot over vi times d omega, which can be written as this, because the material derivative of vi is twice vi dot, so the factor 2 cancels. And now if you recall that rho times vi dot was expressed in terms of the body forces and the traction using the equation of motion that we derived in the last lecture. Now if you recall, the equation of motion was written as rho times vi dot is rho bi plus sigma ij comma j. So we can express this in the expression for the time rate change of kinetic energy. So k dot becomes, and we expand this, to get this expression. Now using this relation which expresses vi sigma ij comma j, that is here, in terms of these two quantities, we can express k dot as like this. And then we can apply the Gauss's theorem here. To express this into an area integral over the bounding surface of the body. And this vi comma j can be written as Lij, that is the velocity gradient tensor. So we get this expression. Now what we see is that sigma ij nj here is basically the traction vector. So we can write the traction here, and this L can be written as a sum of d and w. Now if we look at the last term here, sigma is symmetric and w is skew symmetric, because recall that the spin or the vorticity tensor is skew symmetric. So this becomes a 0 because the product of a symmetric and skew symmetric tensor is 0. So this equation we'll call B, which is the expression for the time rate change of the kinetic energy as a function of time. Also, we had the internal energy, that is capital E, which we'll write as an integral over the volume as rho times small e times d omega. So this quantity small e is called the specific internal energy, which is basically the internal energy per unit mass. So d by dt of E, which basically is written as E dot, becomes simply the integral of rho small e dot times d omega. So let's call this C. So now if you look at equation A here, we have expressions for k dot and e dot now in terms of integrals. So we will substitute these into equation A to get the energy equation that we want to get to. So this is the expression for k dot, and this is the expression for capital E dot. And this here is the right hand side of equation A. So now we clearly see that this body force term on the left and right, they cancel. Also, the traction terms on the left and right cancel. So we are left with a simplified expression. And since this integral is over gamma, we can apply the Gauss's theorem here to express this as a volume integral. And then since all the terms are volume integrals now, I can combine them into one volume integral as follows. And since our omega, the choice of my volume was arbitrary, I could have taken any sub-volume as well. So that means the integrand has to be identically 0 everywhere. And this equation is known as the energy equation, which is also known as the first law of thermodynamics. So let's look at the different terms in this equation and try to get a feel of it. The left hand side term, rho times small e dot, where small e is the specific internal energy. So E dot becomes the rate of change of the specific internal energy. So this includes changes in temperature, because if you provide some energy to a system, it may result in its temperature increasing, or basically the molecules storing the energy as fluctuations. It can result in the change in the phase of the body, that is, storing energy as latent heat. It can even result in the storage of energy as elastic strain energy, and so on. Now on the right hand side, this first term is called stress power. So just like we have a force times velocity, or F dot V, as the power delivered by a force, stress double dot with a D is like a power delivered by stress. So if a stress field results in deformation inside the body, that results in stress work. And since we're talking about rate of deformation, that is deformation happening continuously, so that will result in a stress power. So without deformations, there is no stress power. An example of this would be if you take a rubber ball and try to compress it, that results in deformation of the ball, and that results in some energy being delivered to the material as a stress work. Now if I continuously compress the ball, that will result in power, or the rate of energy, in the form of stress power, that ultimately will be dissipated as heat inside the body. So this stress performing work against deformations is called the stress work, and the rate of that is called stress power. And this second term on the right hand side is the heat flux. And the last term, as we discussed, is the volumetric source, which can include the generation terms such as due to resistance heating in electrical power. So basically what we are saying is that if you perform a stress work, that will result in the increase of internal energy of the body. For example, the increase in temperature. If you provide some heat directly from the boundaries, like conduction through contact with a hotter body, or as a radiative flux, that can again result in an increase in temperature or the internal energy of the body. Or if you put a volumetric source like a heater, like a resistance heater inside the body, that again can result in the increase of internal energy or the temperature of the body. So this concludes our discussion on the energy equation, which was derived through the law of conservation of energy. Now we move on to the tutorial for week 10. So for the tutorial for week 10, we'll be covering topics on the conservation of mass or the continuity equation, the linear momentum equation, the angular momentum principle, and the energy equation. So let's get started. So here is the first problem. So velocity field is given to us with A, B, and C being constants. So in the part A, we have to determine the expression for the density field if the continuity is satisfied. And for part B, we need to find a condition on constants if the motion is given to be isochoric. So let's get started with part A. Since the velocity field is expressed in the Eulerian form, we'll write the continuity equation in the Eulerian form because part A requires to use the condition of continuity being satisfied. So the continuity equation in Eulerian form is rho dot plus Vk comma k times rho equal to 0. Now Vk comma k is simply V1 comma 1 plus V2 comma 2 plus V3 comma 3. So let's find out V1 comma 1 from the velocity field. So this is V1. So V1 comma 1 is an A, and then V2 comma 2. So this is V2. So this is also an A, and V3 does not depend on X3. So V3 comma 3 is a 0. So from this we can get Vk comma k simply as twice of A. So if I substitute this in the continuity equation, what I get is rho dot plus twice of A times rho equals a 0. So now we need to solve this for the density field. So I can write d rho by dt as minus 2a rho. So this becomes d rho upon rho is minus 2a dt, which can be integrated. So this gives a natural log of rho is minus 2at plus c1. Now if I take the exponent on both sides, so this becomes rho as a function of time is e to the power of minus 2at times e to the power of c1. Now since e to the power of c1 is another constant, so we write rho as a function of time as some rho initial, which is a constant, times e to the power of minus 2at. So this completes part A, where we had to find the density expression as a function of time. So let's move on to part B. Now part B says we have to find a condition on the constants if the motion is isochoric. So isochoric motion is when the divergence of velocity is a 0. Now Vk comma k was found out to be 2a. So 2a is 0, which basically implies a is 0. So that is the condition we get on the constant for the velocity field to be divergence free or for the motion to be isochoric. So that completes the solution for problem 1. Let us move on to the next problem. So in problem 2, we are given that the stress tensor, the Cauchy stress tensor, is spherical. You can see it's minus p times delta Aj. In the first part, we have to determine the form which the equations of motion will take if pressure was a function of x and t. And in part B, we have to use the continuity equation to show that the stress power, which is sigma ij dij, can be expressed as this. Actually, this is just P, not a P naught. So let us solve this problem. So since we are working with the Cauchy stress tensor, we'll write the equation of motion in the Eulerian form, which is given as rho times bi dot, that is rho bi plus sigma ij comma j. So we'll substitute sigma ij here as minus p times delta ij. So the equation of motion now becomes rho times vi dot is rho bi plus, now sigma ij comma j becomes minus p times delta ej comma j. Now delta ej is just a constant, so this basically becomes minus p comma j times delta ej, which becomes minus p comma I. So this is our equation of motion for the condition where our stress tensor is isotropic, and this vi dot, by the way, is the acceleration field ai. Now in part B, we have to find the stress work sigma ij dij. So sigma ij is minus p times delta ij, and dij is defined as half of vi comma j plus vj comma I. So if we expand this, this becomes minus p by 2 times vi comma I plus vi comma I, which basically becomes minus p times vi comma I. Now the continuity equation in the Eulerian form is written as rho dot plus vi comma I times rho equal to 0. So this implies that I can write vi comma I as minus rho dot upon rho. So if I substitute this, then sigma ij dij, or the stress work, becomes minus p times rho dot upon rho, and this minus is gone. And this is exactly what we had to show, that the stress work is p times rho dot upon rho, and we have shown that. So that completes the solution to the second problem. So let us discuss the third problem now. There's a case of rigid body rotation where the velocity field is expressed as omega cross x, where omega is the angular velocity vector and x is the position vector of the point whose velocity is being calculated. So for this case, we have to show that the torque, or the total moment about the origin for all the surface and body forces, is given as d by dt of omega j times ij, where I, the moment of inertia, is expressed using this expression. So let us solve the problem. So the angular momentum principle says that the net torque, or the net moment of all the forces acting on the body, is the time rate change of the angular momentum of the body, and both these quantities are calculated about the same point, that is the origin in this case, and the angular momentum vector about the origin is expressed as the cross product of the position vector of the point and the infinitesimal linear momentum, and this we integrate over the complete volume. So in the initial notation, we can write L as like this. So we write this dp as rho times d omega, that's a dm, times the velocity vector. And now since the velocity for this pure rotation case is given to us as a cross product between omega and x, so in the initial notation, if I want to write vk, that becomes epsilon kpq omega p xq. So let's call this 2. Let's call this 1. So we substitute 2 in 1. So we get Li as this. And we have 2 epsilons here. So we can use the epsilon delta identity. But for that, I have to make sure that the second epsilon has the last index as the same as the first epsilon. So I write this as epsilon p q k. So this becomes delta first delta second minus delta first second and delta second first. So let's substitute that. Let's expand this now. We have an xj and xq becomes an xj and omega p becomes an omega I minus xq becomes an xi and omega p becomes an omega j times d capital omega. So we'll do some manipulation. First, let me do it here only. So I'll replace this j with a k because that's allowed. That's an inner product. And then I'll take an omega j out. So this becomes xk times a delta ij minus xj xi, and there's an omega j already out, and this is d capital omega. And since it is a rigid body rotation, then our omega vector is homogeneous. That is, it does not change with position, otherwise we won't have a rigid body rotation. So for the motion to be rigid body, omega has to be homogeneous. So this means I can take the omega j out of integral, and this is rho times this quantity. And this integral was the integral I with the free indices I and j. So we have shown that Li is omega j times Ij, and therefore the net torque becomes d by dt of Li from the angular momentum principle, which is d by dt of omega j Ij. So that completes the solution. So this completes today's session, and this also completes this module on balance laws. So in this module, we talked about the balance or the conservation of mass, the momentum principle, and the energy balance, along with some tutorial problems. Thank you, and I'll see you in the next week where we start talking about constitutive modeling. So thank you very much, and I'll see you next.